Mark. That was a mouthful. Okay, so thank you very much to Mark for introducing me and for having me, and thanks in advance for your attention. So yes, the complexity of sort of spanning two groups. I used to work at PML. I'm now representing the University of Plymouth, but I'm also going to be speaking on behalf of the colleagues I still collaborate with at PML. We still have a very good collaborative relationship. And for you today, I'm going to present some of the research and development that we have done that might be useful to you in terms of this spill response. Is this a tool? Is remote sensing a tool that might be valuable to you? What are its strengths and limitations for detecting and tracking spills? And I'm going to tell you more about my own background in marine plastics specifically. Now, actually, at your disposal are quite a few sensors that I think are worth considering for this kind of work. We have, from the American team, we have Landsat, for example, that has given us data since 1979. It's a continuous mission with new sensors going out all the time, but a mission that has nonetheless been going since 1979, which is incredible. The data is collected at 50-meter spatial resolutions, and what ties a lot of these satellites together is that they're all optical and passive. What does that mean? It means that they can't collect data through cloud. It means there is a confounding factor because light has to travel through the atmosphere on the way in and on the way out, so that's correct for that. And we have to deal with the fact that we can't collect data at night. And sometimes the stuff we're trying to see is not happening conveniently in the middle of the day. So those are the passive sensors. And the ones that I'm going to talk about specific, and I'm going to show you one worldview image. I really rate worldview. I think this is a satellite that I'd like to talk to you guys about. You guys have got money, I don't, but when you want to pass a satellite that costs something, this is the one you might want to consider. It collects data at sub-meter resolutions, very high resolution satellite. But the ones that I use in my everyday and for the research I've done so far are these two. So this is our passive multispectral sensor. Both of these are European Space Agency satellites, so they're responsible for the satellites in space and for the data dissemination. So if you don't like the way the data is sent to you, tell me and I'll go fight with ESA in the park. So this collects, these are both ostensibly terrestrial missions, but what is right next to the land? The coast. And so we have coverage of coastal waters, not the middle of the sea. So both of these collect data at 10-meter resolution, which for free satellite data, free for everyone, is really good. This one is active, so it's radar, doesn't care about cloud, doesn't care about the atmosphere, doesn't even mind collecting your data at night. So it's a bit like a bat, and this one has eyes like us in that it needs light to see. So these are the two satellites I'm going to talk about the most. And you're probably already switched off because you're like, cool, I did not come here to learn about that. So let me just show it to you in a more palatable way. This is a radar image. Where's some rep there, I think? Yeah, you recognize it. That's good. So I took this image from a couple of weeks ago, and this is a radar image. I've used the polarization PVH, don't worry about it, but I've done it in such a way to try and show what we can see from the water without sort of losing the complexity of what we can see. You see that little cluster over there of boats. And actually what's really cool is you can also see a lot of activity in this quite narrow, I'm assuming it's narrow, channel over here. There you go.
I can see you see my yacht.
Well, there you go. There you go. That's one of my checklights. So you can also see some of the features in the water column which are not super clear here, but this is wind shadow. So you can see something about the wind, you can see something about the water, and most importantly, I would say that for marine applications, Sentinel-1 radar data is really good for vessel detection. It's really good for picking up coastal winds and oil detection. So your friend for spills. We're going to move on to something that might make you instantly more comfortable. This is a same-day overpass of Sentinel-2. It's data like our eyes. Here I've created a red, green, and blue composite. I've taken the visible wavelengths of light, I've combined them so that it's an image that we naturally recognize. But remember what I said about the atmosphere. Would you all like to take part in a quick atmospheric correction? If only it was normally this easy. So I've taken away the confounding effects of the atmosphere and it's become a lot clearer. So now we can really see where we are, but you'll notice that that cluster of boats that we saw so clearly in the radar data are quite indistinct in the visible data, and very much so over here. We can sort of see there's something, but nothing with the same level of clarity. And we can also see in the water over here, something we didn't see in the radar, is there appears to be these foam slicks. And we didn't pick that up in the radar. That's what they aren't very good at. If we move out of the visible wavelengths of light into the near infrared, my favorite band, because what can you see? You can see everything on the surface of the water much more clearly. It's still not as clear as radar, but we are now seeing the things on the surface of the water that I'm interested in, like these slicks, in much more clarity. And this is why I used Sentinel-2 all the way back in 2020. We were the first people in the world to demonstrate that you could use this data to detect and classify macroplastic litter in coastal waters. You already know why I said coastal waters. It's because we're using a terrestrial sample. What do I mean by macroplastics? If you've got a plastic water bottle, please hold it up. Right, thank you. When I talk about macroplastics, I'm talking about the stuff you can see, the stuff you can hold in your hands. Microplastics are much smaller than that. They're the fragments. They're below 5 centimeters or millimeters. I can't actually remember, but they're the fragments. And I've underlined classification there because detection is super easy. Anyone can detect stuff. Classification is hard, and I'll prove it to you. I'll prove it to you. Right, here we go again. Sentinel-2 image. Shall we do an atmospheric correction? This is off Da Nang in Vietnam. Absolutely stunning feature that's developed over here as the river water meets seawater. Ignore it though. I want you to look over here. In this little area over here, can you see that? What do you see in there? Nothing much. Shall we do it again? Shall we move into the near infrared wavelengths of light? What about now? Okay. What we can see using Sentinel-2 is that this area is crammed full of things. How do we know what those things are? I happen to have in situ validation data in the form of worldview. Remember I said I really rate the satellite? This is the panchromatic band. It's 0.3 meters in spatial resolution, chasing craters at Christmas. These are floating fish farms composed of plastics, woods, and other mixed materials. Detection is easy. This is the image that started everything. I was actually hired by EDF, the French energy company, to look for floating clumps of kelp after storms so that they could get a warning before their intake valves were overwhelmed by seaweed. There's the Isle of May, a really important habitat for birds and seals. There's the Firth of Forth, so the east coast of Scotland is just over here. And using what we've just learned about the near infrared and what I didn't show you about the shortwave infrared is we developed a floating debris index. And when I apply it to this front over here, can you see the front? Right, keep an eye on the front. It looks harmless. It is in fact not. There are pixels filled to capacity with stuff. And when I did this, I was quite happy. I detected kelp. But when I looked at it spectrally, it didn't look like kelp at all. And thus began my journey, which ended in me understanding that I had detected plastics. Because in the real world, the ocean is empty until it's not. And when it's filled with natural materials, mostly, thankfully, to this day. We've got different types of seaweeds, driftwood, sediment itself, and sea foam. And when plastic is in the wild, it looks a lot like this. It's combined with natural materials. How do we unmix that pixel? So I just want to say, I do use a lot of machine learning, which is a subset of AI in my work. The reason being that I'm trying to be as accurate and I want my work to be as reproducible as possible, but also manually doing this work on a single image takes me half a day. It takes less than a second to run it using machine learning. Is half a day the best use of my time to manually look through for 3 different pixels in an image? I don't really think so anymore. But anyway, so these are spectrally what the natural materials look like. There's seawater. On the x-axis are the different bands of light. So here's the visible light. There's that near-infrared peaking compared to the water. Water is very efficient at absorbing light in the near-infrared. Anything floating on the surface by comparison is going to look reflective. Thanks to the University of the Aegean's Marine Remote Sensing Group, they put out targets that same year, and I was able to finally confirm that what I was seeing was in fact plastics. They look very spectrally distinct, and when plastic is mixed in with natural material, it changes the spectral properties. If you are considering machine learning for any of your own work, I'd like to draw your attention to a NERC-funded service. So it's free for PhD students and researchers in the UK to use. They will provide you with data that has been processed to the standard that you require. You don't have to do your own atmospheric correction. You get them to do it for you, but also they have machine learning specialists on board who will help you figure out, if you need machine learning, how best to make use of the machine learning algorithms that are out there, and they will do that free of charge. So it's a NERC-funded service for UK scientists. And I do really feel like in order to get the results that you can trust, you need to take your expertise and combine it with someone who's already brilliant at this, in order to maximize your understanding. So who in this room, by the way, feels like they've never done machine learning in their lives? Put up your hand. 2 people in the whole room. Okay, 4. So 4 people in the whole room have never done machine learning. Okay, believable. Who of you with your hands up have ever said this email is spam or junk and labeled it so that you don't get that email again? You have just trained the same naive Bayes algorithm that I used for my plastic detection back in 2020. It's very forgiving of small unbalanced data sets. And we looked at 4 different case studies, 2 in the developing world and 2 in the developed world. And we found that we were able to detect plastics with pretty high accuracy. We had some complexity around sea foam. And when pixels weren't full enough, they were being falsely detected as water, or perhaps truthfully. But the good news about this is that it completely invigorated the public. At a time when plastic research was considered a distraction from real science, the inconvenient truth of climate change. So I think it really invigorated research in this area. And it also was included in some policy documents at the time, which for me was a huge win. I like to see my science go into meaningful policy development. Where are we at now? We've added more classifications. We've built up the complexity. We're using slightly different approaches to machine learning, and we're getting slightly scary accuracy, which I try to not believe too much. But we're getting really, really nice results. And I'm continuing to work with NIADAS. Dave Moffat's the machine learning expert there. And what we're trying to build is something called Odyssey. This is not for commercial use. This is not something that we necessarily will be sure will ever make money off of. But what we would like to do is provide absolutely unimpeachable, scientifically excellent, neutral data for countries that need to have a little chat about transboundary plastic pollution. Because sometimes plastic that's on your beach comes from your river or your poor land management practices. But oftentimes it comes from somewhere else. And it doesn't really matter what you do within your own EEZ or with your own MPA. It's the country next door that, probably not on purpose, has created a marine plastic pollution problem for you. So I'm going to give you an example. There's country A at the top and B at the bottom. A is not as well off as B. They really struggle with maintaining the overwhelming amount of plastic that they have from a number of different areas. The plastic they received from other countries, the tourist trade, everything. B is less populated, much wealthier, and is wealthy enough to have been able to consign a whole area of their EEZ as a marine protected area, and one area in particular gets one of the highest categories as a sanctuary zone. So they're able to do that because of the very important marine species that use that for breeding and refuge. So when scientists went out there to document how well those animals were doing now that this was a sanctuary, what they found was not necessarily good. What they found was that the fronts that animals normally target for food were filled with plastic. And the plastic was being transported within what I can only call slicks of ick. And the slicks of ick, when I really looked into this is just 6 weeks worth of detection over time before things got too cloudy and rainy. And I detected a slick another year that was 70 kilometers long. I've never seen anything like it before in my life. I hope to never see it again. But the point is that with almost unerring accuracy, country A's waste is ending up in country B's sanctuary zone. Punitive measures are not going to fix this, but it would be really nice if these two had a bilateral or multilateral conversation where funding was put in place to prevent plastic from happening in B, which actually supports A. because plastic from other countries is not unique. It's a chronic problem and it's growing slowly but surely, but that's not why you're here. You're here because of the acute issues. You're here because sometimes a country gets transboundary plastics from their neighbors, and sometimes they get it from a ship that was passing by and got damaged, right? That's why you're here. Am I right? So what do we do about it? I'm going to talk about my experience with the Express. I think everybody knows this example, okay? This is an image that I like /hate, but what you can see is there's already debris in the water. It's one of the only images I actually found that where it still had the containers on board, and before it broke apart. I was called in to work with the NOAA disaster response team as soon as this event happened. We didn't really get great usable data until about a week later. Now, detecting oil spills in radar imagery is easy. It's a dot, it's fine. So I really wanted to detect the nurdles, but I didn't. What I did instead was I detected the wind field, the wave field, and the oil slicks. And from that, we were trying to understand general transport patterns of where the nurdles might have gone. So I'm going to give you some examples of the imagery, and everywhere that we detected it ending up in it towards a direction, we put a red cross. This, by the way, is a false positive. That's another one of those wind shadows. With machine learning of oil spills, that's a really tricky one to automate out of the detection. Here's a Sentinel-2 image. I'm going to put it back into near infrared so you can see that it's picked up some of the surfactant and some of the slip. All right, we're going to move this along. I'm putting this image in now because the other thing about microplastics, so remember, not macroplastics, nurdles are microplastics, is that they become part of the sediment quite quickly, especially if they're neutrally or negatively buoyant. They'll become part of the sediment quite quickly. This resuspension event was because of inclement weather. So this would have resuspended nurdles that were already out of the system back into the water column to be transported elsewhere again. And so we looked at this for a year. This ship was still spilling oil and surfactants for a year after the first event. But if you have to say to me, where did all the nurdles go based on the data? I don't know. I have no idea. I never once detected a nurdle, much to my despair, because I really looked. But I can tell you the factors that helped transport them. And I did this again for a more recent spill. Does anyone know about this event? It was a Maersk ship. Is anyone here from Maersk or Maersk? No? Okay. This was the day that it happened. Look at the radar image. Do you see big waves and storms? How did they lose 6 containers in this weather? I don't get it. So this is the shipping thing, right? This was the last time those containers were detected. They were starting to float. They were floating, but they were sinking. So they were moving in that direction, which makes sense because you can see the wave field is moving towards the coast, but not in like the dramatic. I'm still very curious, but I mean, I'm not putting that on TikTok because I know that I shouldn't talk in the media about things I don't understand, but I'm just wondering. So we know that after this point, the weather gets super bad. Really, really bad. Perfect storm. We can't detect anything, but we know based on evidence from fishermen, that's where the nurdles went. Fishermen were finding completely full sacks that hadn't been torn, washed up on the rocks, full of nurdles. So this was quite mysterious until we looked in the radar data and the optical data, and we detected really strong internal waves. Do you know what internal waves are? They're waves that happen in the middle of the water column. Sometimes you don't even see them on the surface, from the radar data in particular, but they sit in the middle of the water column, and they'll bring really deep water if they break onto the surface. So they are bringing deep water and taking the nurdles onto the shore. So this was the mechanism of transport, almost certain. Because how else would something that had sunk to the bottom of the sea wash up on the rocks, especially in such good condition? It was the internal waves. These are strong internal waves and they're persistent. So, okay. Satellite remote sensing. is this the right tool for direct detection or direct tracing of your nodal spills? Not yours, of nodal spills in general. I'm going to do something a scientist very rarely does. No, I don't think so. But we cannot underestimate the value that we have gotten, the insights that we've gotten using these data to supplement our understanding of what is happening with those dynamic coastal areas. And if you have nodals mixed with oil or surfactants, yes, we can track the oil, no problem. That's what Sentinel-1 radar data was designed to do. It is perfect for that. So no, but there is still value. I would say the key limitation is not actually even direct detection or lack thereof. It's the temporal resolution. You get an image every 2 to 5 days, depending on where you are in the world from the optical data. And with Sentinel, it's a bit less consistent. You might get an image every 7 days. You might get 4 images a month. You're going to miss the stuff you need to see. So I would say that is actually the biggest limitation. So this is where I really rate the value of the high resolution commercial sensors if you can pay for them. Because not only do you pay for the data that's higher resolution, you can task satellites. You can tell them where to go and where to collect data. As soon as there's a cloud window, they'll get an image for you. So you can task these commercial satellites to go and fetch data for you. But there's another really important role for drones. And this is where I'm going to start presenting on my colleagues' work. And so you'll notice that I'm going to speak slow because I have to be careful. And I'm going to read inside. So this is a project called Hyperdrone. It's an ESA-funded project that my colleague Sir Mata is leading. And he has 3 objectives for this work. The first is to build a spectral data set. This is already 3D available. So if you want to go and see what a spectral data set of plastic looks like in the wild, I think this is one of the only ones that still exists. Proxies for plastic detection on shorelines. It's really hard to see plastics once they're on land, especially if the sand is reflective. And to inform future satellite missions that might want to include some capability for direct plastic detection. What are the current ones missing that we can add to the next generation of sensors? So for those of you who don't know, a bit like NEODAS, if you are considering doing research with a very expensive brand new sensor that you haven't ever tested, that's okay, you don't have to buy it, you can borrow it. So there is a resource called FSF, or the Field Spectroscopy Facility, that works in conjunction with PML and a little bit with the university. And we have used them before. We put one of their sensors on a seaplane and then promised not to land on it. And they just let us loose with it for 3 months and then took it back and went to Tanzania straight afterwards. So you can take these sensors anywhere you want. You can borrow the drone, you can borrow the sensor, you can borrow the guy that flies the drone with the sensor. So there's almost unlimited usage of what you can get if you're doing research and development and you need some support here. Please remember that you can use FSF. Okay, so Asur put out all of these targets. As you can see, there were lots. He put them out on the beach, just off Plymouth. And he found that as hydrocarbons, all plastics have absorption features in the shortwave infrared. Now, the plastic debris index that I use has got shortwave infrared and near infrared information. But as you can see from his work, there's really not a lot of value in the visible bands of light, which we already saw. I demonstrated that to you. We couldn't really see it very well in those wavelengths. And these are not present in materials that are not hydrocarbons. How much time do I have left? Am I okay? Okay. So what I think is amazing is people say to me all the time, okay, so can you discern what type of plastics you're detecting in Sentinel-2? And I'm like, no, it's binary. It's barely confirmed the percentage of plastic material to natural material. I definitely can't tell you what the source of the plastic is. But with this kind of work, you absolutely can. So hypothetically, if you had a nodal spill and it washed up on the beaches and you needed to go and specifically find those nodals so that you could do the cleanups of the nodals on perhaps a beach that's already quite polluted or has other confounding factors, this kind of information is going to be invaluable for knowing how you can discern the nodals from other objects on the beach. So here's a nice example of what he did. He developed the hydrocarbon index. So it's a stepwise process. You mask the water, you mask the vegetation, no atmospheric correction needed. And then you apply the normalized difference hydrocarbon index. Hey presto, microplastics detected. If this is something you're interested in, I highly recommend getting in touch with us, sir. Not only is he incredibly accomplished and a ninja with drones, he is also one of the nicest people you could ever work with. And sometimes that's all the joy you need in a project. So please get in touch with us, sir, if you have any questions or you're interested in this for your own work. There's more than that. That was macroplastics. We're going to talk a little bit more about microplastics. So this has been also led by scientists at Cook Marine Laboratory, where they've used Landsat 8, which you met, and Sentinel 2, to look at suspended sediment. So remember I showed you that image and I said there was inclement weather and that sediment got mixed up again. There is a lot of evidence, thanks to them, that that sediment contains microplastics. It is an excellent proxy for microplastics. At this stage, measuring is good, but we can almost take it for granted. It's going to be there. It's going to be carrying the microplastic load. So they've tested this, they've proved that, and they've looked at it off the coast of Italy, where what they found was the transport of those microplastics in the sediment was a given, but where it went and how it went was based on things like the wind direction and the strength of the river outflow. Really nice for holidays, not so great for microplastics. There's a strong river influence. So this is an example, a rarer example of the plastic pollution that's on your beach came from you, it's from their own rivers. Very high river influence, especially between Tramontana and Pila, because of the extra influence of the lagoon, and SPM there for the first time was proven to be a really robust proxy for microplastic load. And you can read all about it in these papers, but you can also go straight to the source. So Liz Atwood has been leading this work for yonks, and she is the expert on SPM. So that's very South African of me. And then Emma has been leading this work in the UK, so she's been applying Liz's techniques to the UK. And we've been looking at SPM and microplastic load outside the Plymouth Sound. What am I doing? I'm doing something I have no business doing, by the way. I should not be looking at microplastics. I have no business, but it is currently my side quest. And the reason for that is because I am working on a project called Gill Winds. And I'm using my friend satellite radar to look at onshore winds that might be carrying things we don't want to breathe in, but medically proven absolutely are. We know that microplastics and nanoplastics, this new thing, it's great, it's super theoretical and probably really, really bad for us. They accumulate in our lungs, but also the lungs are such a nice gateway to all of our other organs. So it does mobilize out of the lungs with horrible implications for human health. And the primary sources of the microplastics that you and I, all of us, breathe in tend to be terrestrial in origin. Tire particles, our clothes are made from plastic. We're breathing in those microplastics every time we move, every time we do our washing. The thing is, the high microplastic load in surface waters, those microplastics can get ripped out by aerosolizing winds that are about 3 to 5 meters per second. Do you know what that's called on a Beaufort scale? A brisk breeze. That's sufficient to take those microplastics out of the surface waters and put them into breathable air. Now, why do you care about that? Well, I would say that you care about that because I learned about this because of a study done on volunteers doing oil cleanups on beaches that did not wear appropriate PPE. We developed asthma as adults after doing cleanups on beaches far away from the initial oil spill because of aerosolization of oil droplets, which contain things I can't pronounce, but I'm sure you guys know what they are. They sound horrible. Yeah. Can you pronounce those all?
Now you just like Vtex.
Vtex.
We all know what it is.
I have Vtex. Right, okay.
Vtex.
Yes, Vtex. Okay, so not only can they carry oil droplets, they can carry radioactive materials and other toxic components. In fact, you can have a toxic reaction to a harmful algal bloom that's happening on the other side of the city if the winds are just in the wrong direction. And on that really happy note, I will say that if you do have a spill and you don't have access to on-the-ground wind data, please consider getting in touch, and we can quickly get some Sentinel-1 winds for you so that you can know which direction the wind is blowing right up against the coast and at what speed, so that you know how at risk your team is of breathing in VTEX, okay, and other things. I want to quickly, if I've got time, I want to show you something really interesting. So I added this slide after the fascinating talk this morning, which was about the oil spills. My students in my master's class with this study, they used Sentinel-1 data to map an oil spill, which I don't know if you guys know about. It happened off Tarawang in Indonesia in 2019. It was a very big spill, and an oil well that broke there just in this area here. The square kilometerage of water was covered with oil over a 3-month period was 262 square kilometers over that period. But they noticed while they were doing this work, this little oil well over here, it's just tightly spilling little bits all the time. So they tracked it for 4 years, and it's in a 4-year period, it surpassed this big acute spill that got all the media attention. So sometimes it's not just where in the world you have the spill to get the media attention, it's how high you can get away with it. So that is just something to bear in mind, and you can't hide from Sentinel-1 because that's where they spotted it. Okay, that's me. Thank you so much for your attention.
Oh, I don't know whether to cut the wrist now, but never mind.
I know. My
Anyway,
research is not filled with joy all the time.
Not all, no, indeed.
No.
Questions for Lauren? Professor?
I'd like to make a comment fantastic with what you've shown. That big cable data on radioisotope transport, and you've just shown in second last slide radioactive elements.
Yes.
So there's a million ton of plastic released per year as sort of a macro litter. That's maybe a surface of 100 square kilometers. As they degrade, it's probably closer to 500,000 to 1 million square kilometer every year.
Yeah.
And because the avidity for radioisotopes is so high, we had an observation not published because the nuclear sector, we never let people know what we know, but we know the release highly dilute from Fukushima traveled to our body, piggybacking on that interaction surface.
That's right.
Now we have added every year and continue, probably more than 1 million tons per year, an interaction surface that behaves like a sediment, but not really like a sediment. We have added to the compartments that we need for risk monitoring, something that's never existed.
Yeah.
There is a question still behind it. What is the closest natural occurring element that might behave like these nanoplastics, and would there be a surrogate? We know from biodiversity hotspots, that's also where the plastics are. So I think something in the nutrient sphere travels with it. And then
I'm so glad.
Bracket would be, that's where your remediation needed to focus on the hotspots. And can you predict them already?
What if your hotspot is basin scale? So one of the projects we're looking at is has anyone heard of sargassum?
Yeah.
The seaweed, right? There is your very good medium that acts like plastic, picks up the heavy metals, picks up the radioisotopes, picks up Vibrio cholera. I've read about it before. I did not think I would be studying cholera in this area, but here we are. It is, when combined with plastic, especially, it is one of the most efficient transporters of cholera and other heavy metals, basin scale. And the plastics, as you say, act as these incredible vectors for all these nasties, including at the microscopic scale. So I didn't want to tell you this because I didn't want to be like that Debbie Downer, but like those microplastics that we're breathing in, the biggest source of them is untreated sewage. Yeah. And microplastics are very good at growing diseases, microorganisms, E. coli, Vibrio. And they're also very good at containing other chemicals that, you know, we definitely don't want to breathe them in. So they're acting as vectors. I'm not touching that. I'm not qualified to touch that. All I can say is that we're breathing them in. But on global scales, plastics are now starting to interact so closely with other materials that we can't even tell them apart anymore, but we know that when they act in concert, they're absolutely, well, we suspect that the consequences are going to be devastating. No one studied this yet, so we're looking at this. But yes, it's an excellent question.
Yeah.
And, you know, when they looked at the load of plastic in the ocean, before they understood the role of wind, they were like, where are all the missing microplastics in the surface waters? We don't know what's happening to them. Because water, plastics are through the entire water column, but all these microplastics in the surface, well, we know where they are now, they're now in the atmosphere. And they're traveling hundreds of thousands of kilometers if the winds are strong and high enough, or they're traveling 10 kilometers to where they They aren't degradable. Do you mean if they didn't fragment?
Would they be lying around like a creek on flora?
Yeah. Yes.
So
Yeah.
should we actually not pursue a whole degradability, accelerated degradability of plastic?
Oh, I don't
Well, I think
know
we're
about
beyond,
that.
I think we're beyond the stage of
Yeah,
developing that.
I-
We need to clean up what we've got out there and stop the rest of it going in.
I would say that
Hmm.
instead of taking that approach, rather think about removing them before they fragment. And if
Yeah,
we are
absolutely.
going to create plastics that break down,
Yeah.
let them be something that can be eaten.
I would just say, maybe
Yeah.
we should not pick plastics that do degrade.
Oh, I see what you're
Oh, I
saying.
see.
Yeah, yeah.
Degrade,
So that they don't
But
break
it
down.
depends what they
into
degrade
smaller
to. But I think that's slightly a topic which
We
we
are
want to
having
cover.
coffee.
We are covering that topic. We're covering that
Yeah.
topic tomorrow.
Yeah, yeah.
Any other questions for Lauren?
Oh.
Josh,
Firstly, fantastic talk. I absolutely love that. So brilliant.
I thought it'd be right up your street.
Yeah. So on that point of response from acute spill, what can we do as an industry? And it might be sort of open to the room really. What can we potentially add? So we've obviously got dispersants with oil spills that we can add to help. But is there potential we can apply a dispersant which might pull the pellets together or help just better track it?
I mean, the thing about nurdles is they're sneaky, right? So they sink super quick. You think about it, and when you see pictures of nurdles, they often look like they'd be floating in a nice chunk on the surface. And that's why I thought I can detect these no problem. But that's not true at all, right? They immediately sink. They become neutrally buoyant or negatively, well, they are naturally negatively or neutrally buoyant, and then they're lost. So if you had something that caught them, almost jellified them into something that did float in a big aggregation before that happened, I mean, absolutely. Because then not only, even if we didn't detect them, if it washed up in a big gelatin chunk, how much easier would that cleanup be? But I guess the scale and you'd have to have it happen almost almost before the disaster.
But actually the point is, and I'm going to talk to Rob,
Yeah.
is there a role for herders when you have a plastic spill and you've identified where they are? I'm going to leave that one hanging in the air because it's a thought for another day. Yeah.
Yeah. I will.
Sorry.
Yeah, I mean, there's so much to do. I still feel like we're right at the beginning
Oh
of
no, we
this,
got
right?
loads to do.
But I will say,
That's why we're collaborating.
yes,
Share the load.
exactly. Share it. Tell you how far or not far we are with the research on our side as well. But I think also having signatures on plastics produced so that we know, it would just make that identification so much easier if we knew where in the shortwave infrared to look specifically. We've been talking about this for fishing nets because they're really flipping hard to detect, if not impossible, unless they've got nice big polystyrene floats in them. But can you make that in the shortwave infrared with a tag so that we can spot them easier? Because like ultimately it doesn't benefit anyone to have ghost nets floating around. It doesn't benefit the fishermen either.
Anyway.
Yes. Our material is fingerprint.
Ah,
It could never be counterfeit.
yeah.
Combinatorial logic. Totally correct.
Yeah. So if that were legislated, we'd be able to trace and tag all of the plastics. There
Andrew.
we go. Sounds amazing.
Good thought. I'm interested in the satellites. Can they actually identify nanoplastics?
We can't even see them yet truly with microscopes. We use lasers.
Well, you've already got the hyperspectral imaging cameras that are already doing that.
Yeah.
But surely, that's the area really that we need to be working at in the UK.
Yeah.
Because at the end of the day, it's industry that's producing the plastics, which is going into the water. If we could see the water.
Oh yeah.
10%.
We need to intercept it before it gets out there.
Yeah. or just,
I was just interested in whether we could image the waters in the rivers to see if is the technology not there on satellites.
so no, not yet. And also the the hyperspectral sensors you're talking about tend to have about 30-meter spatial resolution, which is 3 times more coarse than the data I've been showing you today. But ask me in 5 years, because to date, we haven't really even seen nanoplastics in a lab. They're still considered a theoretical particle to a large degree. But getting sensors that can find proxies or detect them, space lasers, oh God, my husband's going to kill me, space lasers, then he loves it. But yeah, then, ask me in 5 years' time.
But we
Right.
already have the waste collection centers that can actually identify the different plastics.
Yeah.
Yeah.
And sort them.
Yeah, at the nano stage, we tend to be looking intracellularly.
Yeah.
So that we're
Yes.
talking about
Mm.
so much smaller that we've never actually directly seen
Yeah.
them.
We're gonna have to, we need to move
But
on.
I would love to
because,
talk more about that.
at
because that's
lunchtime,
absolutely where it's going.
Yeah.
Yeah.
Lauren, thank you very much.
Sure, thank you so much.